Welcome to a new video. This one's going to be the final on the Year 12 topic of trigonometric ratios. So the main focus today, we're going to be looking at the graphs of sine, cosine and tangent in more detail than before, some of their key definitions and properties, and we're going to conclude by looking at how we can transform the graphs of these trig functions with some relatively simple transformations based on what we did in Chapter 4, Transformations of Graphs. Before we get on to that, here's a little warm-up for you, questions 1 to 4, and as you can see, these are just a recap of Chapter 4 work on transformations. So pick your brains, try and remember how transformations work, and if you're stuck, have a look back through your notes at Chapter 4. So right now, I'd advise you to pause the video, try these, use your notes to help you if you need, then press play and see the solutions and how to do them afterwards. Okay, so let's have a look together now at question 1. So from questions 1 all the way through to question 4, we're just considering one point P, which is at 1 minus 3, which is on the curve of y equals f of x. So all that's happening is the curve is undergoing a single transformation. We're just wanting to consider how the original point P moves from being P where it was to P dashed where it ends up after the transformation. So for question 1, we're talking about the transformation of minus f of x. So how do we transform f of x to minus f of x? Well, I'll remind you of this, but I'll just bring up a little quick crib sheet in the form of a table here, just to refresh your memories. So if we look here, it's this one. It's a reflection in the x-axis. Now, how I taught this to you is if we go from f of x and the change happens outside of the brackets, it affects the y-coordinates in a more common sense way. So f of x to minus f of x, the y-coordinates are multiplied by -1. And so it's a flip of the y-coordinates. In other words, it's a reflection in the x-axis. And so all that happens here is it affects the y-coordinates, which are multiplied by -1. The x-coordinates are invariant, so P, we stay here, I didn't want red, I wanted a black colour. So P, the y-coordinate of P stays at 1, but the y-coordinate gets multiplied by -1. So minus 3 multiplied by -1, that becomes 3. For B, to go from f of x to f of minus x, we're looking here. It's a reflection in the y-axis. The x-coordinates are multiplied by -1. So if the change happens inside these brackets here, it affects the x-coordinates, and it happens to affect them in an opposite to common sense way. So I'd be thinking of this as rather than the x-coordinates being multiplied by -1, they're divided by -1, which in this case happens to be the same thing. But anyway, 1 therefore becomes -1. The y-coordinate isn't affected at all, so that stays as -3. For part C, describe in mathematical language each of the transformations in parts A and B. So for part A, it's a reflection in the x-axis, as it says here. And similarly, but slightly different, part B is also a reflection, but part B, it's a reflection in the y-axis. Let's have a look at question 2. So question 2, again, I'll remind you of the crib sheet if you'd prefer. There it is. These are the rules. So to go from f of x to 2f of x, the 2 is outside of the brackets, so it affects the y-coordinates only in a common sense way. So the y-coordinates are doubled, the x-coordinates are not affected. And so the point P, the x-coordinate is not changed, but the y-coordinate is doubled. So -3 doubles to become -6. For B, the change happens inside the brackets, involving the x, so it affects the x-coordinates, as I've said, in an opposite to common sense way. So rather than the x-coordinates being doubled, which is what it looks like, the x-coordinates are going to be halved. The y-coordinates are not going to change. So the x-coordinate of 1 halves to become just 1/2. The y-coordinate stays at -3. Part C, describe the mathematical language of each of transformations in A and B. So A, what I'd say for A is, because it gets, the y-coordinates are doubled, it's a stretch parallel to the y-axis. So for part A, it's a vertical stretch Give the scale factor as well. The scale factor is 2. And as if this didn't say it clearly enough, you might also want to say it's just parallel to the y-axis. So that's how I describe part A. And describing part B, it's a compression. So you could say compression, or again you could say it's a stretch. But because the x-coordinates are affected, it's not a vertical stretch, it's a horizontal stretch. So even though it's compressed, you can still call it a stretch. In the same way as GCSE transformations, you can have an enlargement of a fractional scale factor which shrinks the shape. It's a similar sort of logic here. So this one, it's a horizontal stretch, but this time it's scale factor of 1/2. And because it's a horizontal stretch, we can say that the stretch is parallel to the x-axis. So let's have a look at question 3. Question 3, we've got transformations where the change is inside the brackets, so again this is going to affect the x-coordinates. Here's the crib sheet again if you need it. This first one, if a change happens inside the brackets, it affects the x-coordinates in an opposite to common sense way. So rather than adding 2 to the x-coordinate, we're going to actually subtract 2 here. So P dashed, we subtract 2 from the 1, 1 minus 2 is -1, y-coordinates aren't affected, so y-coordinate stays at -3. For part B, we have x minus 2, so actually we add 2 to the x-coordinate. So the x-coordinate here is 1 plus 2, so P dashed is at 3 minus 3. So it's not a shift where it's a compression or a stretch, it's just a shift of the same sort of curve from one place to another. So in terms of describing it, it's actually a translation of the curve. So question C, describing these transformations, part A could be described as a translation of the function of x by the column vector of -2, because it goes 2 to the left, and 0, because it's not going up or down. And for B, again B can be described using a translation. So for B, it's a translation of the curve f of x, this time by the column vector +2, because we moved 2 to the right, 0 on the bottom, because we're not moving up or down. Question 4 here is very similar in fact, but here you can see the change from f of x to these. The change is happening outside of the brackets, so this is going to affect the y-coordinates. For the final time, here's a little copy sheet if you want to have a look at all of the transformation rules. But here, because we're taking f of x and just adding 2 to each and every thing, it just gets shunted up 2 units in the y direction. The x-coordinates aren't affected, So the x-coordinate of p dashed is the same as the x-coordinate of p, which is 1, but we add 2 to this minus 3. So minus 3 plus 2 takes us to minus 1. For part b, it's the whole of f of x shunted down by 2 units. The x-coordinate stays as 1, but this minus 3 goes down another 2 and becomes minus 5. So describing these mathematically, I can describe the transformation in A as a translation, again because it's not a stretch or a compression, it just moves from one place to another, it moves down, so it's a translation by the vector 0 at the top, because it's not moving left or right, it's just going down, sorry what I'm talking about, it's going up, sorry, by 2 units, so it's positive 2. Whereas for B, because it goes down, that's going to be a translation by the vector 0, minus 2. Again, 0 at the top, it's not moving left or right, it's just going down, so minus, going down by 2 units. And that's the warm-up completed. So now we can have a look at the main bit of this session. So first of all, we're going to have a look at graphs of the trig functions, starting with a graph of y equals sine x. And so we've got a grid for you in the notes. See your grids here. I'm going to have a go, possibly foolishly, at sketching this myself. My sketching is absolutely shocking, as you'll see. But I'm just going to give you a little method for sketching sine. You need to know that sine is a waveform, so it oscillates, goes up and down, regularly and repeats. What you can do for sine, if you ever forget what the critical values are, and you've got a calculator at hand, is just try multiples of 90 and just plot them. Then you can work out the next by just plotting a curve through your points. So for example, if you try sine of minus 180, you get that it's 0. Okay, so sine of minus 180 is 0. You can then try sine of minus 90. And get that's minus 1. So we can draw minus 1 here. Sine of 0, the next multiple of 90 along, we get that that's 0. So again, we can plot in 0. Now you can try the next on your calculator for yourself. I'm not going to do the calculator again, but if you try sine 90, you get that that's 1. And sine 180 is 0. So I have this waveform here with a smooth curve. It just keeps going up and down in the same way. So the next point would be there. Then we go here, up at 450, and down again at 540. So here goes nothing. I'm going to plot it, or at least attempt to. So with a smooth curve going through these points. Bit of a wobble there. Ugh, that's pretty bad. Through that one and down again. Ah, it was going so well. So that's my rather wobbly, jagged sketch. So to save my embarrassment any further, here's a perfect one I just used some software to make. That's what you should have in an ideal world, if you could draw graphs perfectly. Maybe you can, I certainly can't. So that's the graph of sine x. So let's just think about some properties of the graph of y equals sine x. So the first thing I'd suggest that we might want to notice is the domain. So what range of values can x take? The domain just means what values x is allowed to take. X can be any real number. There's an infinite number of x values you could take, down from near minus infinity to positive infinity. This is just a section of an infinite number line. Sin x would repeat this curve again and again and again for infinity, both to the left and to the right. So the domain is infinite. It's any real number. The range, just to recap on what the range means, the range is the values that y can take. So if you look here, y goes from -1 to 1 inclusive, because at some points it is -1 and at some points it is exactly 1. So we can say that the range is where y is from -1 to 1. As well, period is 360 degrees. The period, if you were doing physics, the period is the wavelength, essentially. And so the wave repeats every 360 degrees. And so I'll try and show you this here. So if I just have a look, for example, from 0, goes to a peak, back to 0, then a trough, back up to 0. That's one complete cycle. It takes 360 degrees to do one complete cycle. As well, a not so obvious fact is that the sine of -x is the same as minus sine of x. Now, a function that follows this is called an odd function. Sine x is an odd function. I wouldn't worry too much about this, but it's worth me just mentioning it now. An odd function as well has rotational symmetry about the origin. If you were to put a pin here, that's the pivot, and rotate this graph 180 degrees about the origin, it would look exactly the same. So an odd function has rotational symmetry order 2 about the origin. So sine x is an odd function. Next up, let's think about the graph of cosx. Now, cos stands for cosine. So here's the grid, and again, in the same way, you can sketch cos, if you forget the critical point, by just taking multiples of 90. So if you were to try cos of minus 180, you'd get that it was -1. Cos minus 90 is 0. Cos of 0 is 1. Cos 90 goes back down to 0. And cos 180 is -1. It then repeats the same wave pattern. So then sketching it with a smooth curve if you can. Like you've seen already, I struggle with this. Just do a smooth curve through the dots. A question in the A level wouldn't ask you to sketch it and give you lots of marks for accuracy in terms of looking if you do a smooth curve. So don't worry too much about if your curve is a bit wonky. Just make sure it goes through the critical values correctly. So something like this. And again, just as a cheat, here's one I created earlier with perfect waveform on it. So let's have a look at the critical points and key definitions and values on this graph of cosine x. What makes it special? What are its properties? So first to mention is, just like the graph of sine of x, the domain is all real numbers. It's got an infinite domain. X can take any real number value. The range, just like sine of x, is exactly the same. The range goes from -1 to 1 inclusive. So y can take any value from -1 to 1. The period, again, like sine, is 360 degrees. Okay? And if you look here, the graph of y equals cosine of x is actually symmetrical about the y-axis. And so if you were to take the graph of cos of minus x, which, using the laws of transformations, that flips it in the y-axis, that'd be the same as cos of x itself, because it's symmetric in the y-axis. Now, functions that have symmetry in the y-axis are called even functions. For example, y equals x squared, that's an even function, because it has symmetry in the y-axis too. Looking at these first 3 bullet points, you should see that the graph of cosine shares very much the same properties as the graph of sine. This is because 1 is essentially a translation of the other. If you imagine cosx, okay, being moved 90 degrees along, it'd be the same as the graph of sine of x. So in other words, what I'm saying here is if you took cos and shifted it 90 degrees to the right, it's not x plus 90, remember, it's x minus 90. Inside the brackets, it's opposite to common sense. You'd end up with sine x. And this actually is one of a few different identities based on the fact that sine and cosine are just translations of 90 degrees of each other. And so, just as a little extra, you might want to make a note of these extra things in yellow. Okay, the one I mentioned here was cos of x minus 90 is the same as sine of x. And so these are all based on the fact that cos and sine have the same period, the same range, the same domain, the exact same shape, just one is 90 degrees away from the other. And so these will be seen time and time again in the A level, well worth remembering now if you can. So let's move on to the graph of tanx. So for tanx, on your notes, I've put here dotted lines. So these dotted lines are actually for the asymptotes. This is where the graph of tan will approach either positive infinity or negative infinity. So I'm going to show you here, if I just take 0, what's the tan of 0 going to be? Well, tan 0 is 0, so I can put 0 there. 0, 0. What about tan 45 would be? Tan 45 would be 1. What's tan minus 45? That's minus 1. So if I go halfway in between 0 and 90 at 45, that's 1. And down here that would be minus 1. What about something more? Let's say tan 70. Or maybe tan 80 even. 5 something. That's even higher. That's about 5.5 times higher than this point. So tan 80 is going to be well up here. And if you have a look at tan minus 80, that's minus 5.67. So the same thing here, but down below. Now as you get closer and closer to either 90 or minus 90, let's try for example tan of 89. It just explodes. It goes towards infinity. And if you were to actually try tan of 90 or tan of minus 90, your calculator will freak out and just vomit in your face. So that's to say that tan 90, tan minus 90 is undefined. So what's happening here, I'll try and draw it, not that my drawing's good, is it's asymptotic at minus 90 and 90. It does sort of blow up. An asymptote is where the curve gets infinitesimally close to a straight line without actually ever quite touching it. And what you'd find actually with tan is this pattern repeats again and again and again. So this line here, I might actually try and cheat, so forgive me for my lack of credibility. I'm just going to try and just show you that actually this will just repeat again here, again over there, again in between these two asymptotes, and again beyond 450, and would repeat forever, essentially. Now as you can see, my lines are wonky. Here's one I made earlier, with perfect curves. Now let's consider the properties of tan x. So, first of all to mention, like I mentioned before, vertical asymptotes. These dotted lines are called asymptotes Like I've said, this is where the curve gets infinitesimally close to them without actually quite touching them. They become more or less parallel as you get close to the asymptotes. So algebraically, the first one's at 90, and they repeat every integer of 180 degrees on from 90. So 90 plus 180n, where n is an integer, z stands for Zahlen, which is the symbol for integers, okay? So if n is an integer, 90 plus 180n is a sequence that generates the x values where these vertical asymptotes are. For domain, now this is quite technical language which I'm going to explain to you. For domain, the values that x can take are infinite. X can be any real number. This dash means apart from. So x can be anything apart from, then what's in these curly brackets tells us what x is not allowed to be. So x is not allowed to be where these asymptotes are. So if I factorise out a 90 from here, that becomes 90 brackets 2n plus 1. Dot dot means such that where n is an integer. So x can be anything apart from 90 plus 180n, where n is an integer. So this is just mathematical language explaining that x can take any real number apart from where x happens to be an asymptote. As well as this, the range of values, that's a mistake by the way. I'm not going to correct it, I'm going to leave this in there because that's just me being a total numpty here, apologies. The range is y is any real number. The range is y can be anything, okay? Y can be down towards negative infinity, y explodes up towards positive infinity. The range of y is unbounded. Y can take any value for this function of tan. So, moving on, let's have a look at a worked example here, finding values from trig graphs. So, using the fact that cos 60 is 0.5 and the graph of y equals cos x, find two more values of x for which the cos of x equals 0.5. So to do this, here's cos x from before, and I'm going to show you whereabouts cos x is 0.5. As you can see here, and you can use this one on your notes, you could just draw a horizontal line across at 0.5, like so. So, first off, we're told that cos 60 is 0.5. Okay, so if I just drop down here and label this in as 60, we can use the symmetry of the cos curve to work out the other values. There's a few ways of thinking about it. Your brain will work differently to mine. The way I see it is 60 is just 30 degrees away from the x-intercept. So it doesn't take too much of a stretch of imagination to see that the other values, using the symmetry of a curve, must also be 30 degrees away from the intercept. So for example, this one here must be minus 60. This one here is going to be 270 plus 30, that'll be 300. This one here will be 450 minus 30, that'll be 420. And so all you need to pick is another two values. So if cos x equals 0.5, just using this graph here, x could have been, apart from the 60, x could be minus 60, which is this one here. X could be 60, which is already given to us. X could be 300. X could be 420, and so on and so on. So all you need to pick there is just any two. Doesn't matter which two you pick, just any two. There's 3, pick 2 of those. Which example 2, we're talking about the tan function. So using the fact that tan 60 is root 3 and the graph of y equals tan x, find two more values of x for which tan x is positive root 3 and tan x is negative root 3. So again, here's a graph from before. So this is the graph of tan x. So what we're thinking of here is whereabouts is the y value, root 3, because it's a graph of y being tan x, and whereabouts is this y value equal to negative root 3. So we can just add in two vertical lines, one at positive root 3, one at negative root 3, like so. And think about where these cross. So we're told tan 60 is root 3. Okay, so this one here is going to correspond to a value of 60. Likewise, using the rotational symmetry of the tan curves, this one here, that's going to correspond to a x value of negative 60. Now, one thing I didn't mention before about the property of a tan graph, which is well worth noting down, another property of a graph of y equals tan x is the period of the graph of y equals tan x is 180 degrees. It repeats every 180 degrees. So that's well worth considering. And we can use this to our advantage to do this question. So where tan x is root 3, we just need another two more values where tan x would have been positive root 3. And so this one here is at 60. Add another 60 onto that. That one's going to be 240. Well, again, you can use the repeating symmetry. Another way to think of it is this is 30 degrees away from the asymptote here, 30 degrees away from the other asymptote on the same side. 270 minus 30 would be 240. Well, again, in the same way, minus 90 minus another 30, 30 degrees from the asymptote on this side, that would be minus 120, and so on. So x, you could have picked minus 120. You couldn't pick 60, that's been given. You could pick 240. Next one along, that one would be 420. So any two of those values. For tan x being negative root 3, using the fact that this one's at minus 60, we could pick x being minus 60 here, which is 60 degrees away from where it crosses the x-intercept. And again, just using the period as being 180, we can just plus or minus multiples of 180 from this minus 60. So the first one here, where tan of x is negative root 3, that one would be minus 240. So we could have x as being minus 240, minus 60. This one here would be 120. 300. This one here would be 300. And this one here would be 480. And so on, infinite solutions. All you need is just two. So just pick any two of these. I think I'm going to go for minus 120 and 240 for where tan x is positive root 3. And for tan x being minus root 3, I'm going to go for, let's just pick 120 and 480. It's up to you. Next and finally, question 3, part A, we need to sketch in the interval from 0 to 360 the graph of y equals cos x minus 90. And again for this one, I'm going to cheat and use the previous sketch we did. And so if I just take the previous sketch, which is here, now this isn't within the same range. This is from minus 180 to 540. But bear with me, I'll just truncate it in a moment. So for this one, this is a graph of y equals cos x currently. Okay, the graph of y equals cos of x minus 90, from cos x, just remember your transformations of functions. What sort of transformation would map from this to that? The changes happened inside the brackets, so it affects the x coordinates in an opposite common sense way. So rather than the x coordinates being subtracted 90 from them, we're going to add 90 to each x coordinate. So it's going to be a transformation translation rather, in the positive x direction. I'm going to move 90 along and not up or down. And so what's going to happen here is this curve is going to be moved 90 degrees along and it's going to be here. Now these are both the same colour, so I'm just going to colour code the one we're interested in. So I want to just highlight the graph of y equals cos of x minus 90, which is this one here. And what I can do in a moment is just, as I say, just curtail it, so we're just looking at from 0 to 360. So this is the curve I'm looking at, and to be fair, it did say from 0 to 360, so let's just knock some of this off. You wouldn't be marked down if you left it, to be honest, but just so I'm not showing off by plotting too much. That's 360, and on the other side, let's just leave it a tiny bit beyond 0. And that'll do. I'll just include that this is the x-axis. For part B, state the coordinates of any local maximum or minimum points. So basically where is at its peak and trough. So the maximum, first of all, is here. So we've got a maximum point where x is 90 and y is 1. We have a minimum which is down here, where x is 270 and y is minus 1. And part C, write down the period of cos of x minus 90. Because it's just a translation, it's not been stretched to a greater wavelength, it's not been shrunk to a smaller one, the period is still 360 degrees. And if you spot that what sort of graph is this, it's actually been translated to the graph of sine x. I mentioned this earlier, cos of x minus 90 is the same as sine x. If cos is translated 90 degrees to the right, it becomes the graph of sine x. Just one more to do, and then we're done. Question 4, sketch the graph of y equals 1 plus 2 sine theta in the interval from 0 to 360. So we're going to start off by just with a coordinate grid. Our parent function, we're going to start off with sine theta, then translate this step by step. So first of all, how could we go from sine theta to 2 sine theta like we have here? So from sine theta to 2 lots of sine theta, the change is on the outside of anything to do with sine. It's just sine theta multiplied by 2. So the y coordinates would be doubled. So this would be a stretch scale factor 2 in the y direction. So this blue curve, as it stands here, that's the graph of y equals 2 sine theta. Then finally, what we're going to do is we're going to take 2 sine theta, then plus 1 to the whole thing. So the whole thing is going to shift up 1 unit. So rather than the intercept being at 0, I'm going to shift the whole thing up so that the intercept is at 1. And so actually what we have here is not the graph of y equals 2 sine theta, because you've shifted it all up. This is now the graph of y equals 2 sine theta plus 1, which is exactly what we wanted. And to add a bit more detail onto it, you'll see that the maximum is where it's at 3, the minimum is where it's at -1. So the graph of y equals 1 plus 2 sine theta, just to avoid any ambiguity, because we've got 2 curves on here, I'll just highlight it in yellow. Look at this blue one here, as such. So it's a 2-step transformation. First of all, go from sine theta to 2 sine theta, double your y coordinates, stretch it parallel to the y-axis. After that, just add 1 to the whole thing, shift it up in the y direction, 1 unit. Now it's over to you guys to try some of these questions. Guys and girls, I should say. Let's go to page 197 and 198. It's exercise 9G, questions 3, 4 and 5, then skip onwards to 7, 8 and 9. Sketch them as accurately as you can, but don't worry too much about if you've got a wobbly hand, just do your best. If you're unsure, ask me, consult your book to get the solutions, double check as you go, and keep working hard. Thanks so much for listening. If you got to the end of the video, do take care, and hope to see you all again very soon. So thanks for now, and goodbye.